You are probably wondering how we got here. We were challenged to design a wind turbine which should rotate clockwise viewing from the wind direction. It should produce its maximum power at tip speed ratio from 3 to 8 and be tested at 4 different wind speeds, 6, 8, 10 and 12 meters per second. But the most important constraint was the size. The turbine should be 3D printed as one part, so no two students can take it home at the same time, unless they live together. And the size of the 3D printing box is 100 by 150 by 400 millimeters. To calculate the power coefficient, we need to consider two things. First, the power generated by the turbine, which is obtained during testing. Second, the power available in the axial flow of air through area of 400 mm diameter circle. That left us with three options. First, small and safe 400 mm two-bladed turbine. Second, one-bladed turbine, which has a bigger blade but requires a counterweight which is really tricky to design. Recalling the power coefficient, the longer the blade, the better the performance. That's exactly why we went for the third option. We decided to design a turbine which has two blades 400 mm each printed folded side to side to fit into the box. With this in mind, we considered aerodynamic performance and structural integrity. But the main challenge then was to figure out how to achieve our goal, keeping the blade as one piece all the time to satisfy single part criteria. And we did figure it, but first,
in order to build the most efficient blade given our design choices and the constraint Roman just mentioned, 4 design parameters had to be selected. The airflow section, the chord distribution, twist angle distribution, and finally the optimal tip speed ratio for our blade. For the airflow section, our objective was on the one hand to find a thick airflow section with the best lift to drag ratio possible, and on the other hand to find an airflow which did not suffer from low Reynolds number aerodynamic effects such as separation bubbles, as this would negatively impact our performance. Given these considerations, 2 airflows caught our eye. The SD7003, as it had a very clean lift to drag curve at low Reynolds number. And secondly, the SG6043, as this airflow had previously been used for this exercise and performed extremely well. In the end, we chose the latter airflow section, as the SD7003 led to an unreasonably high chord distribution due to its low camber. Regarding the chord and twist angle distribution, we identified 2 school of chords available to calculate them: the Schmidt's formula versus the Bates formula. To establish the one most appropriate for our project, we created a MATLAB script performing blade element momentum BEM analysis and found that the Schmidt's formulae gave the best results for our blade. We also used our MATLAB script to compute the TSR, which would give the best performance for our blade, and found that it should be equal to 6. Finally, the route was designed to give a smooth transition from the airflow section to the nose cone whilst ensuring the required cross-sectional area for the structural integrity of the blade, as Juliano shall explain now.
So, Loris has found that from an aerodynamic point of view, this design would give us the power that we need. Now this is indeed a proud moment. But first, what I need to do is to evaluate the structural integrity of the turbine blades. Because at the end of the day, this small turbine will have no less than 300 kilograms of force pulling on each blade. Okay, so we need to ensure that 2 main conditions are met. On the one hand, the stresses due to both centrifugal and aerodynamic forces should be less than the tensile strength of the ABS at every point. To calculate these stresses, the blade was discretized into 40 sections, and the stresses at each cross-section due to the centrifugal force associated with the previous elements from the tip inwards were found to be well below the yield strength. The main challenge, however, was the root, which, as small as it is, has to withstand not only the highest centrifugal force, but also the largest direct stresses due to bending. For this purpose, we opted for an ellipse cross-section, which was found to meet all the constraints. On the other hand, we had to make sure that the tip deflection due to bending was small enough to not interfere significantly with the previous aerodynamic calculations. To calculate this deflection, a discretized version of the virtual work method was used, together with the idealization of the blade as a cantilever beam with various cross-sectional areas. And the findings suggested that this small deflection would not alter the turbine aerodynamics to a large extent. Hence, we are now ready to proceed to the next step and design the nose cone.
So the nose cone design was broken into two elements, the shape of the nose cone and the connection between the two halves. For the shape, we looked at whales. Whales have to travel huge distances combating against drag and optimizing their energy usage. And nature has provided us years of evolution to get inspiration from. In 2009, researchers at the University of British Columbia published a study on the optimal fineness ratio in large whales to minimize their drag. We took this study and calculated that our fineness ratio should be about 2. This means that the length should be twice as big as its diameter. We then considered optimizing the 3D printing space. So splitting the cone in half and printing the two wings next to each other will allow us to utilize the length of the whole 3D printer. Then we considered connecting the two halves together, and we did so by erecting two rods and connecting them with a ring that would allow for rotational mobility but restrict them from being separated. And now,
for our main bio-inspired augmentation, we look to the skies for inspiration. We design our wingtips based on birds which curls up their feathers during gliding to produce more lift. We went to find the best birds in London.
At the wingtip, the difference in pressure between the lower surface and the upper surface causes air to bleed from the lower surface to the upper surface. This results in induced drag and reduces the lift generated. The winglets reduces the pressure gradient at the wingtips. This results in a smaller vortex generation and hence results in a lower induced drag, overall increasing the lift generated. After extensive research, we decided to go with the Fournier wingtip. The Fournier wingtip is a sharp-ended winglet. The sharp edge reduces the size of the vortex and increases the effective span of the blade. This deflects the vortices further away from the blade and further reduces induced drag. The biggest challenge we faced in designing the winglets was the dimensioning. Particularly because of the size of the turbine we were designing, there were no available resources giving us a reference geometry or dimensioning of existing winglets. And lastly, but most importantly, we wanted our winglet to improve our aerodynamic efficiency. Now moving on to Maurice to see what our result holds.
Looks like it's working, guys. Alright, so it's 4 a.m. We just finished the CAD model and the drawings. This is, we 3D printed the turbine to half scale, and we're gonna test. Hopefully it's been the right direction. Let's go, let's go!
The aluminium hub used to fit the turbine onto the test mount is manufactured from a solid cylindrical aluminium block. First, a lathe is used to drill a hole. Next, we use the CNC milling machine to create the hexagonal outer shape of the hub. The finished product from the 3D printing is sanded to ensure a smooth surface over the wind turbine, especially the blades. This ensures that flow is smooth during operation. We sanded the turbine using sandpaper of progressive coarseness. The process is repeated multiple times as needed. The last part of the manufacturing process required us to rotate one half of the turbine and bolt it together with the other half. After this was done, we had to secure the two halves together using 5 bolts and washers on each side. The testing was conducted at the Donald Campbell wind tunnel. The wind turbine performed exceedingly well at wind speeds of 6 and 8 meters per second, reaching a peak power of 27 and 67 watt respectively. Approaching 9.5 meters per second, we noticed vibrations at the wingtips, causing loud noises to be heard. The RPM reading was stagnant at around 2000. In the end, we managed to get a peak power reading of 119 and 200 watts at 10 and 12 meters per second respectively. This gives a maximum power coefficient of 1.74 and a tip speed ratio of 7.75. The turbine blade failed shortly after the testing.
Wait, it's still in one piece. Whoa, okay, bro.
The failure point was found to be near the mid-span of one of the blades. This corresponds to the location of one of the shifted layers which was likely formed by the 3D printing process. Also, the vibrations we noticed during the testing could be due to the blockage effect of the wind tunnel. Due to our two-bladed design, the blockage was changing as our blade rotated. We could potentially improve our results by looking into the three-bladed design for our wind turbine.
And with that, we just have 3 more words to say. Group 7, out.